Myths about how and why the Industrial Revolution happened are told often. Historians and lay people alike love to speculate about what made Europe the only place it could start. And while that's a useful discussion to have, I think it misses the forest for the tree. The Industrial Revolution couldn't have happened without something even more fundamental: the so-called scientific revolution. Or more precisely, the rise of the scientific method as the dominant framework for thinking about the world. The scientific method, in its simplest form, is this: we observe the world, then build models based on those observations to predict the future. We test those predictions against reality. If the model fails, we revise or discard it and build a new one. Enlightenment-era Europe wasn't the only place or time where empirical philosophy developed. Not even close. From India, we only have commentary and condemnation, as the Bharhaspatya Sutras are lost. Still, even from that, it's clear that what we might call the Charvaka school was materialist, empiricist, and embraced skepticism. It was fundamentally incompatible with Hinduism and Buddhism, and thus disappeared. China had Mohism, the teaching of Mozi. While most of his thought revolved around utilitarianism, with focus on ways to achieve peace, there was a strong undercurrent of skepticism, as there always is with utilitarianism. The school fizzled out, as Confucianism became the de facto state philosophy/religion of the Kingdom of Heaven. The strongest contenders to proto-science were Arabic philosophers from the Islamic Golden Age, with Ibn Sina, known in the West as Avicenna, Abu Ali al-Hasan ibn al-Haytham, aka al-Hazen, Abu Bakr al-Razi, also called Rhazes. This only lasted until the Mongol invasions unmade the Islamic Golden Age. The trauma turned to conservatism and handled all philosophical innovations as bid'ah, which before that civilization-shattering invasion meant banned, heretical religious novelties, but only religious ones. So why Europe? What made the conditions right for empirical methods to not just appear, but to endure? I would argue that a big reason for that was glass. Because glass is what made most scientific instruments possible, and more importantly, affordable. Thus, empirical thought was able to deliver results, guaranteeing its place without need for faith or people proselytizing it. Glassmaking was to Europe what porcelain and silk were to China, a high-skill, high-innovation craft making luxury goods. If you trace the centers of cutting-edge glass production, you'll find they map almost perfectly onto the regions producing groundbreaking science, regardless of which shore of the Mediterranean or which age you contemplate. That seems unlikely to be a complete coincidence. India was also exposed to alchemy from the Islamic Golden Age. However, Indian philosophy emphasized enlightenment and detachment, turning away from worldly concerns. The idea of obsessing over physical transformation or perfect materials didn't align with that spiritual focus. In addition, artisan work in India was considered low caste. Tinkering, glassblowing, alchemy, these weren't noble hobbies. So, the kind of eccentric upper-class tinkering you saw in Europe, where gentlemen built telescopes and burned things in glass flasks, would have been scandalous in India. In China, the story's different. Glass existed, but it never held cultural weight. It was often seen as the poor man's jade, a fragile imitation of something more sacred, permanent, and prestigious. It never became the thing to have, like Murano glass did in Europe. The earliest glass objects known to archaeology are beads from Egypt, dated to around 2500 BC. Of course, it's unlikely those were the very first ever made. These early beads weren't what we typically think of as glass today. They weren't transparent or crystal clear, but more like roundish, colourful droplets. Probably discovered accidentally as a pretty byproduct in metalworking slag. Despite their crude origins, the technique spread quickly. Within a few centuries, glass beads show up all over the ancient world, even as far as China. Elaborate glassmaking evolved primarily around the Mediterranean. By the Hellenistic period, artisans were already making fairly elaborate glass pieces, using tools, moulds, and mandrels. They'd even figured out how to colour glass by alloying it with trace materials. Copper dissolved into glass made it blue, manganese purple, and so on. The glass in question was soda lime glass. That name comes from the additional ingredients added to the fine-grained quartz dust that is sand. As a crude recipe to 8 units of sand, you need to add 1 unit of soda, sodium carbonate, 1 unit of lime, aka limestone, calcium carbonate. These additives are crucial. They lower the temperature needed to work the glass from over 1500 degrees Celsius, which would melt iron glassworking tools, to around 800 degrees Celsius, making glassworking possible. Then, around 50 BC, someone in what is now coastal Syria invented glassblowing, the practice of dipping a metal pipe into molten glass and inflating it like a balloon. This was a game changer. For the first time, people could make hollow, intricate glass objects relatively quickly, and we still use this basic technique today for one-of-a-kind glassware. Of course, the tool needed for this, the blowpipe, wasn't trivial to make the old way. Crafting a 1.5 metre, 5 foot, iron or steel pipe is no small feat. It meant hammering out a long, thin strip of hot metal, rolling it around a mandrel, like a straight tree branch, applying flux to prevent oxidation, and then hammering the overlapping edges together until they stick, a process known as forge welding. The next major breakthrough came sometime before 100 BC, again in the Levant. Transparent glass. The problem was that natural silicate sands aren't chemically pure. They contain impurities, most often iron oxides, colloquially known as rust, which tint glass green. That's not ideal if you want clarity. You can even today see some of this if you look at a cheap sheet of window glass edge on. The solution was adding pyrolusite, manganese dioxide, a black mineral also used in glazing ceramics. When added to the glass mix, it effectively steals oxygen from the iron oxide, converting ferric ions to ferrous ions, less rusty rust, which is much less colourful. This made clear or colourless glass possible, opening the door to things like window panes and transparent tableware in the late Roman Empire. Still luxuries, but technically feasible. Since glass doesn't rot, doesn't rust, over time the amount of glass going around increased, making glass more affordable as the years passed. The critical step in democratizing glassware was the invention of the blowtorch. More precisely, the original meaning of the word, the blowpipe torch. I don't mean modern propane blowtorches, but their original namesake. A hollow pipe, even ceramic pipe or reed stalk will do, used to blow air over an oil lamp flame. That stream of oxygen makes the flame hotter, smaller, and more precise. This tool allowed people to work glass without a full forge or large workshop. Suddenly, the kind of delicate work needed for lenses, thermometers, and other instruments could be done on a much smaller scale, with a setup you could operate today in your college dorm room. Now we have glass and the know-how to work with it. Let me tell you why it's important for creation of proto-science, science, and for the creation of modern industry. The true beginning of glass objects used for experimentation goes back quite early, all the way to the 1st century CE, with Mary the Jewess, an alchemist from Alexandria, who among other things invented the bain-marie, which posterity named after her. Also known as water bath double boiler. It's made of 2 concentric vessels with a layer of water between the inner and outer wall. It's used to heat delicate materials over uncontrolled heat sources, like an open flame, without burning them. Since water never exceeds 100 degrees Celsius, the inner container stays safely below that limit. Glassblowing has remained, to this day, one of the most affordable and flexible ways to create scientific glassware, especially for poor chemistry students and resourceful tinkerers. Why glass? Because it's practically perfect for chemistry. It's chemically inert. It doesn't react with most substances, nor with most cleaning agents. It's transparent, letting you directly observe reactions as they happen. Transparency also helps when shaping it, allowing you to see what you are doing while building multi-layered objects, making it ideal for building setups like distillation columns or reflux apparatuses. It's relatively easy to work with. No rare materials or massive infrastructure needed. Even today, in the age of standardized, mass-produced lab glass, specialized or rare glassware can still be prohibitively expensive. A soxhlet extractor, for example, might cost anywhere from a few hundred to several $1,000s, depending on size and complexity. Which is why, even now, many chemists know at least the basics of glassworking. Finally came vacuum technology, the root of all evil in physics, arguably causing the creation of AC waveforming, computation, and quantum mechanics. And again, it couldn't have started without glass. Well, I guess Hanover is going to be a recurring place of cursed science. First with cursed scientists with Herschel's last episode, now with cursed scientific wisdom this episode. It began in 1865, in Hanover, with a man named Hermann Sprengel inventing the Sprengel pump, the first pump capable of creating ultra-high vacuums. By that I mean that there isn't just less air in the vacuum than outside, creating a pressure differential. I mean that there are scarcely any air molecules in there, so you can do ultra-pure chemistry with no rusting or other contamination. Fire single electrons across a vacuum without them getting knocked off course by stray gas atoms. So here it's how you make it and how it works. First, you make a thin glass tube. Heat a not-so-thin glass tube until it gets soft. Then pull. The hot section stretches and narrows, just like pulling taffy. Then, you drip liquid mercury from the top into the pipe. Since it's narrow, each droplet of mercury acts like a piston moving down. Any gas in the pipe between 2 droplets will be dragged down the tube. To make it draw vacuum, you just connect a pipe to the side of the thin section. If any air wanders into the vertical part of the piping, it will be caught between 2 falling droplets and be dragged out of your vacuum chamber. If you don't have a death wish, don't do this the old-fashioned way. You should use vacuum pump-rated silicon oils instead of mercury. Those won't poison you and make you die horrible ways. But you might then ask, what do you do when you already drawn a vacuum? Can you ever stop dripping mercury or oil? Yes, you can. You heat the pipe part connecting your vacuum chamber to the pump, then pinch it, sealing it shut. This last part is a huge convenience upgrade. When your entire vacuum system is made from glass, it can be constructed as a single, continuous piece. That means you don't need any vacuum-tight gaskets or metal flanges. There is no risk of leaks creeping in from joints when you don't have joints. If you've ever dealt with maintaining vacuum seals, you know they're a nightmare. Every seal is a liability, but with glass, you just heat it, pinch it, seal it, done. This is what made early vacuum experiments not just possible, but elegant. The same material that formed your chamber could also form your seals. A vacuum system that could be closed off permanently, without moving parts or screw threads. It worked with only hand tools and heat. This is what made the creation of the first commercial light bulbs possible. Those were just the first vacuum tube-based electrical devices. Soon people found out that since heat is just molecular motion, if you heat stuff, the surface will shake some electrons off. You can do all sorts of fun stuff with those shaken loose free-flying electron. Here is some of the things people got up to. In 1895, Wilhelm Conrad Röntgen used static electric fields to accelerate said electrons and whack them real hard into a metal target. The surface hit by them became real hot. Not white hot, not UV ray producing hot. It produced X-rays. Without vacuum, there is no X-ray. 4 years later, Jonathan Zenneck used a similar idea in a less excessive manner to spray the phosphorus-coated surface of a tube with a thin stream of electrons. The stream was yanked around by a pair of metal plates hooked up to AC, allowing the visualization of AC current and creating the first oscilloscope. Oscilloscopes got way more refined over the years. Still, they are the calipers needed to measure AC systems even today. Vacuum tube-based electrical devices were necessary for experiments that led to the scientific madhouse that is quantum mechanics. In 1914, the Frank Hertz experiments shown that energy level in atoms is quantized, meaning it comes in fixed units. You can have 1 unit, 2 unit, etc. But you cannot have fractional amounts of energy, like 1.1 unit of energy, or 2/3 units of energy, just whole units, which is as absurd as a car being only able to go with whole units of speed, like 1 miles per hour or 2 miles per hour, but not 1.5 miles per hour. Then the Davison-Germer experiment in 1923 confirmed the wave-particle duality of electrons, meaning that they can be material particles sometimes and waves at other times depending on the circumstances. In 1926, Kenjiro Takayanagi builds a working 40 by 40 pixel display, basically the first ever TV screen. And in 1939, a Tanasov-Berry computer is built out of vacuum tubes. In short, without glass we wouldn't have quantum mechanics. To know how to make semiconductor devices for computation, and much, much more. And even if we somehow were divinely gifted with such knowledge, it would be little use without vacuum technology. As without vacuum, stray gas molecules bashing into stuff makes the intricate manufacturing of modern semiconductor chips impossible. In essence, Without glass, there would not be even a hint of the trappings of modern industrial civilization you see around you, because there would be no science. After all, without experiments, science is just hot air, just another school of philosophy, and frankly, not even a particularly convincing one. Unlike other philosophies, science is constrained by the scientific method. It doesn't reward pleasing ideas. It doesn't care if something's easy to believe or emotionally satisfying. Despite what most so-called science journalists claim, science is not a series of big ideas revealed by geniuses. Science is a process of discovering more and more about the objective reality, done by a long tradition of experimentalists, doing the icky, manual labour adjacent work that is so despised by the managerial and upper classes and the general entrepreneur worship of our times.